Hello and welcome back. It's me, Kamal, your friendly neighborhood calculus nerd, and today I have a very interesting trig integrals. I actually love investigating trig integrals, and today we have a really cool one. We have the integral from negative to positive pi by 4 of cosine to the 2 times n minus 1 of x minus sine to the 2 times n minus 1 of x divided by cosine to the 2n of x plus sine to the 2n of x dx, where n here is a positive integer greater than 1. And it turns out this thing evaluates to a very nice, very surprising closed form. And to begin the solution development, we'll first take note of the fact that we're dealing with only even powers of the sine and cosine functions, so the integrand is an even function of x. So we'll write this as twice the integral from 0 to pi by 4 of cosine to the 2 times n minus 1 of x minus sine to the 2 times n minus 1 of x divided by cosine to the 2n of x plus sine to the 2n of x dx. And next up, let's factor out the cosine terms upstairs and downstairs. Therefore, we have twice the integral from 0 to pi by 4 of cosine to the 2n minus 2 of x times 1 minus the tangent to the 2n minus 2 of x divided by cosine to the 2n of x times 1 plus tangent to the 2n of x dx. Immediately we see some cancellation taking place. So we're rid of the cosine to the 2n terms, and we're only left with cosine to the negative 2 of x. Now cosine to the negative 2 would be the squared secant function, so we have twice the integral from 0 to pi by 4 of 1 minus tangent to the 2n minus 2 of x divided by 1 plus the tangent to the 2n of x times secant square x dx. Now we can make the obvious substitution of letting tangent x equal u, which implies that secant square x dx equals du, and this further implies that the target integral I equals twice the integral from, as x approaches 0, we have tangent 0, which is 0, and tangent pi by 4 is 1. And we're left with 1 minus u to the 2n minus 2 divided by 1 plus u to the 2n du. And now for another transformation, I probably should have performed it in a single one, but it's okay, perfectly cool. We're going to let u to the 2n equal t, which implies that u is of course equal to t to the 1 by 2n, and this further implies that du is equal to 1 by 2n times t to the 1 by 2n minus 1 dt. And the limits of integration are clearly not bothered, so we now have twice the integral from 0 to 1 of 1 minus, now let's see, u here is t to the 1 by 2n, and this thing is being raised to 2 to the 2n minus 2, terribly sorry about that, divided by 1 plus t, and we also have 1 by 2n because of the differential element, and we have t to the 1 by 2n minus 1 dt. So we have some nice cancellation taking place, and we have 1 by n times the integral from 0 to 1 of 1 minus, let's see, we have 2n minus 2 divided by 2n, so that would be t to the 1 minus 1 by n divided by 1 plus t times t to the 1 by 2n minus 1 dt. And now we can just perform the multiplication here, and then we have 1 by 2n times the integral from 0 to 1 of t to the 1 by 2n minus 1 minus t to the 1 minus 1 by n plus 1 by 2n minus 1. So we have some cancellation here. In the denominator, again, we have 1 plus t dt. Okay, cool. So negative 1 by n plus 1 by 2n is 1 by n times 1/2 minus 1, right? So this is the hardest bit of the video. 1/2 minus 1 should be negative 1/2. Yeah, I remember some mathematics. So we have I here equal to 1 by n times, now making use of the linearity of the integration operator, we have First, the integral from 0 to 1 of t to the 1 by 2n minus 1, terribly sorry about that, dt divided by 1 plus t. And we also have negative integral 0 to 1. What exactly? We have t to the negative 1 by 2n, right? Yeah, that's about it. dt divided by 1 plus t. And now what? Well, there's this really cool integration result I derived a while back, link in the description below, and it states that the integral from 0 to 1 of x to the s minus 1 divided by 1 plus x dx equals the digamma function at s minus the digamma function at s by 2 minus log 2. And for the case of the first integral, we have s equal to 1 by 2n, obviously. And for the second integral, we have s equal to 1 minus 1 by 2n. So this is pretty cool. It implies that the target integral I equals 1 by n times, what exactly? We have digamma 1 by 2n minus digamma 1 by 4n minus log 2 and, oh, terribly sorry about that, much better, minus sign now, so we have digamma 1 minus 1 by 2n plus digamma, multiplying that thing by 1/2 gives us 1/2 minus 1 by 4n plus log 2, so we have this nice cancellation of log 2's. Funny thing, the original exploration actually had a plus sign in the numerator, so there was cosine to that something plus sine to that same something, and that gave a really nice result in terms of an assortment of digamma functions. But this one's very, very cool because, well, we don't have the 2 times log 2 as in the former case, and there's also a property of the digamma function we can actually make use of to render this even nicer. So what do we have? Well, we have I equal to 1 by n times digamma 1 by 2n minus digamma 1 minus 1 by 2n plus digamma 1 by 2 minus 1 by 4n minus digamma 1 by 4n. And for the first two terms, we can make use of the sort of reflection formula for the digamma function that I often forget, so I'm just going to derive it right here in front of you guys. We have gamma s times gamma 1 minus s equal to pi times the cosecant of pi times s. So taking the logarithm gives us log gamma s plus log gamma 1 minus s equal to log pi plus log cosecant pi s. And now differentiating with respect to s, because the logarithmic derivative of the gamma function is the digamma function. So we have digamma s and a minus sign because of the chain rule. Digamma 1 minus s equal to log pi differentiates to 0. And we have 1 by cosecant pi times s, and the derivative of the cosecant function is we have negative pi because of the chain rule, and we have negative cosecant times cotangent. So that's cosecant pi s times cotangent pi s. The cosecants cancel out, and we're left with, for digamma s minus digamma 1 minus s, that's exactly what we have here. For s equal to 1 by 2n, we just have negative pi times cotangent pi s, which is, again, very cool. So this implies that the target integral I equals 1 by n times a bunch of stuff. That is digamma 1/2 minus 1 by 4n minus digamma 1 by 4n minus pi times the cotangent of pi divided by 2 times n, which is a very cool looking result indeed. And for the case of a plus sign in the numerator that I was originally investigating, we have a result in terms of another nice assortment of digamma functions, and minus 2 log 2 is in there as well. Log 2 has a habit of popping up at various places where it honestly doesn't it shouldn't be. It never looks like it's supposed to be there, but that's the habit of log 2. That's the history of log 2, the mysterious nature of log 2. Anyway, that's enough for today's solution development. I hope you enjoyed the video. Be sure to like and subscribe. Do drop me a follow on Instagram as well. And in case you like the effort I'm putting into my work, consider supporting me on Patreon. Thank you. See you next time.